and check. So Justine
Yep, he's here.
here, and then Gong Jun is also here. Mingxuan Chen is also here. Xuan He is here. Timothy Wong is also here, and then Jintao
No, I think.
is not here yet. Okay, but
Yep.
he's the last one, so maybe we have some time.
Sure.
So yes, thank you very much for joining this session on active transport and transit. I am Giancarlo Sparadi from the University of Tokyo, and I'll be hosting you today. And the first presenter is going to be Justine Brylle Pajarin, talking about optimizing bicycle lane networks for improved cyclist travel and comfort in the presence of vehicle traffic. So a little bit change in the program. I also originally asked to send me a short bio, but since some of you have not done that, please introduce yourself when you start your presentation. So Justine, whenever you're ready.
Okay. Can you hear me? Hello?
Yes.
Okay. I'm just going to share my screen. Can you now see my screen?
Yes, we can.
Okay. Thank you. So, okay. A pleasant day to everyone here. I am Justine Brylle Pajarin, a master's student from the Urban Transportation Research Laboratory of the Department of Urban Engineering at the University of Tokyo, and my supervisors are Professor Takami and Professor Paradi, who's here. So I will be presenting my research on bike network design with a case study applied in Pasig City, the Philippines. So this will be the outline of my today's presentation. So as a background, during the COVID-19 pandemic, the Philippine government promoted active transport by funding projects and programs, standardizing designs for bike facilities and infrastructures, defining agency roles among other government agencies in the Philippines, and educating for safer interactions on the road, especially for pedestrians and cyclists, who we see are the most vulnerable among the others. So the establishment of bike lanes led to a rise in cyclists, as well as cycling accidents, with a 48% increase in Metro Manila from 2019 to 2020. Moreover, some bike lanes are disconnected, and as normalcy returns after COVID, the need for bike lanes is being questioned in some areas in Metro Manila, which became the most congested metropolitan area in 2023. So this leads to the formulation of the research problem, which focuses on designing a bike network that considers the existing traffic, the road space, and budget constraints, with the goal of enhancing cyclist comfort and ensuring connectivity of links that have bike lanes. So for the scope of my research, I selected Pasig City in Metro Manila as my study area due to its dedication in promoting cycling, its institutional capacity, and the city having an existing bike network, which has been established even before the pandemic. So in my literature review, international benchmarks for cycling infrastructure are primarily from Western countries. So Crow from Netherlands identifies these 5 key elements of cycling-friendly infrastructure, which are found to be consistent across these various guidelines. On the other hand, the recent policy shifts in Eastern countries like Korea and Singapore now emphasize moving people instead of cars and creating cycling-friendly environments. So creating a cycling-friendly environment has been explored in previous studies, especially with bike network design. And these studies used optimization problems in building bike networks according to their selected goals, such as maximizing accessibility, comfort, or bike travel, or even minimizing cycling risks to prevent further accidents for cyclists, as well as others that interact with them. Bikeability evaluation tools are also widely recognized, including this Bicycle Compatibility Index. So this assesses adult cyclists' comfort when riding under different circumstances, particularly in geometry and operation conditions of the road. So parameters that improve cycling comfort are the bike lane width, the curb lane width, and the area parameter or the surrounding land use development of the road. So these parameters, as you can see, have minus sign indicating that they lower the BCI value and consequently provide better cycling lower levels, as you can see in this table. On the other hand, a road that allows faster speeds, has higher traffic volume, and parking turnover rate decreases cycling comfort levels. So originally developed in the US, BCI is now widely used and accepted and has been used in other studies as well. And in this study, I also adopted the BCI for bi-level optimization. So the upper level objective for this model actually focuses on the change in BCI before and after the bike lane introduction on the selected links. So the upper level selects the links for bike lanes, then adjusts the corresponding road space in those selected links, which then results in traffic volume calculations and changes due to the trip assignment in the lower level. And results from this lower level are then used to calculate the BCI before and after, which will then identify the objective function value for this model. Then each set of links forms a subgraph to ensure connectivity of links, and this must stay within the budget imposed on the model. So solving for the optimization problem, I used a genetic algorithm which has been used in previous studies in optimizing bike networks. So this generates an initial set of solutions used to obtain values of the objective functions in the lower and upper levels. And solutions with the optimal value will undergo crossover and mutation techniques that will generate offspring solutions which are more likely to improve the values of the objective function. So this cycle continues until the maximum number of iterations is satisfied, which will then further identify the most optimal solution in this framework. So now I developed and incorporated in this model this network of Pasig City as shown in this figure, which includes primary roads in yellow links and orange links that are secondary roads in the city, and a few tertiary roads which are only created for the purposes of traffic assignment in the lower level of the model. So these network roads feature classifications such as the road class, number of lanes, road widths, road speeds, and capacities, whose minimum and recommended requirements were derived from existing reports for Metro Manila, Google Maps, and OpenStreetMap, among others. So trip demand, on the other hand, was obtained from the TomTom Move Portal's OD analysis. So these zones that I developed in QGIS, as shown in this figure, were incorporated into that portal to obtain the OD travel demand for the network. And figures obtained were used in the traffic assignment level of the model. So in that particular trip demand, I used the morning peak hour of the area, that is around 7 to 8 o'clock in the morning. So now we move on to redesigning roads when a bike lane is introduced. One of the road diet solutions done in urban areas in the Philippines involves lane width reduction, as you can see in this figure, where this road was 10 years ago, around 2014, and later on, this road diet solution of lane width reduction was actually implemented in this area, as you can see here in this particular side of the road. So this is the road diet solution I adopted in this study. So assuming lane widths in all roads measure 3.35 meters, lane width reduction applies only to roads with 2 or more lanes. So for 2-lane roads, a temporary road diet is proposed since the bike lane width doesn't meet NACTO's minimum requirements of 1.5 meter for conventional bike lanes. So this proposal follows Japan's Ministry of Land, Infrastructure, Transport, and Tourism's guidelines, which recommended bike lanes of at least 1 meter wide where space is limited. So for other lanes, both the bike lane width and curb lane width meet the minimum requirements. So incorporating all mentioned processes into the optimization model and assuming that there are no existing bike lanes in the network, we obtain this resulting solution. So left figure shows the solution, which was affected by the changes in traffic as depicted in the right figure. So as we can see here, the roads that have green links in the right figure, which indicate a reduction in traffic volume, are those that are selected for the solution in the model. So roads here are selected for bike lanes if there's a potential to reduce traffic volume. On the other hand, roads without bike lanes that can be found near the solution, such as this one, show an increase in traffic volume, indicating the red links in this figure. Moreover, the presence of a critical link in the solution provides or shows a link that is weakens the network connectivity, as the removal of this particular link will violate the connectivity constraint that is imposed in the model. On the other hand, observations on roads with bike lanes have reduced speeds. So as we can see here, the roads that have greener links have reduced speeds, and those are the ones that are built with the bike lanes. So this is consistent with existing studies showing the impacts of building bike lanes on motor vehicle traffic. Moreover, from the perspective of transport planners and authorities, this budget constraint feature of the model can be taken advantage to determine which links should be prioritized to immediately improve cycling comfort in the network. So in this case, this area is the first one that will be built with bike lanes, since this area provides more comfort. And once you increase the budget limit in the model, the network continues to grow until it reaches the other side of the network in this case. Finally, the proposed road diet solutions were applied to the existing bike network. So a field survey was actually conducted in the study area and showed that many roads do not meet the minimum bike lane width and curb lane width requirements. An example of which is shown in this figure, where a bike lane was added without necessary adjustments to the lane widths as shown here. So the proposed road diet solutions address this issue, adjusting the lane widths to evaluate their impact on the existing network. And here we see when these proposed solutions were applied, we saw slightly improved cycling comfort levels in roads with bike lanes, as shown in this table. So this is apart from the motor vehicle traffic being able to use the curb lane width more efficiently after the curb lane widths were adjusted. And applying further the model to the existing network also reveals additional bike lanes in green links in this figure, which align with the city's expansion plans. So the city plans to build more bike lanes in these blue links, as you can see here in this figure. However, we see here that some links are actually tertiary roads, which are not considered in the model. Nonetheless, we see in this particular table that cycling comfort improves with the proposed road diets and the addition of these optimized roads as a result from the model. So for the conclusion, this research applied the model to Pasig City, which enhanced cycling comfort levels. So traffic volume parameters between the lower and upper levels of optimization significantly impact the selection of roads for bike lanes. Then roads with bike lanes show reduced speeds compared to when they had no bike lanes. And additionally, budget constraints can help transport planners and authorities plan their network according to their timelines. So while conducting this study, a number of limitations were encountered. So first, the BCI tool, even though it's widely accepted, it was not locally calibrated due to time constraints. Then the other one is secondary sources, which underestimated OD travel demand on congested roads really affect the solution, considering that there's a particular road in the network where initially it was not congested, but the existing condition of that particular major road in the network is really congested. So it really affected the solution to this particular study area. And furthermore, while there is a connectivity constraint, it only checked the link connections and not the quality of the network's connectedness. Hence, the solution having a weak connectivity, particularly having a critical link in a major road in the network. Furthermore, tertiary roads were also excluded from bike lane construction, as this was based on the input from an officer that I interviewed in the transportation department of the Philippines. Finally, cyclist demand, which was attempted to be incorporated in the model, was not considered due to a lack of available OD data, especially for the cyclists. So given these limitations, several recommendations are proposed to improve for future studies. So this study is actually one of the few applications of network design problem in the Philippine setting, which I hope can be followed to continuously improve cycling environments in Philippine cities. So that's it for my presentation. Thank you very much.
Thank you very much, Justin. So we have two questions in the chat. I will read them out loud. So thank you for your interesting talk. It seems on the bi-level model presented on page 10 includes at least two modes, so cycling and vehicles. So is mode choice how the passengers select between cycling and vehicles involved in the study? So are you using mode choice to model the mode that actually users use?
For this study, I haven't included mode choice, considering the lack of data for doing so and conducting the study on determining the mode choice in that particular study area. But I think it also is important to consider mode choice to determine which routes and should this cyclist will go to when they use bicycle around the network to travel in the network, and as well as if they will even use bicycles, considering that right now in the Philippine setting, cycling trips are relatively low compared to other cities, global cities that are really bike friendly. But I think in the future studies, conducting mode choice is a good idea to determine further how many trips can come from cycling in this particular network.
Thank you. And then the second question is from Mehmet. So why is connectivity enforced for the bike network? So bike infrastructure is usually not connected in most cities.
Connectivity is actually important, considering that if you're a bicycle, if you see that, for example, there's no bike lane in that particular road segment of the network, it will be less comfortable for you to cycle on that part of the road. And actually, in the case of Philippine cities, bicycle comfort can be considered as one of the factors that impede other people to cycling. So if we consider this connectivity factor in building bike networks, this will further encourage people to cycle, and in the long run, we envision to have more cycling trips.
Okay, Thank you very much. So, are just about in time. So let's wrap it up here. Justine, thank you very much. I would like to move up
Thank you.
to our next presenter. Gong Jun is going to be talking about a multi-period asymmetric transit frequency design. So whenever you're ready, please go ahead. And please remember to introduce yourself before you start.
Okay, can you hear me?
Yes.
Okay, let me share screen. Okay, good morning, everyone. I'm Jun from I'm Jun, a PhD student from the University of Hong Kong. Today I'm happy to share with you our topic about multi-period asymmetric transit frequency design. Also, my supervisor is Professor Cedar. Okay, let us turn to the introduction. Public transit is important for the daily commuting. Transit frequency setting plays an important role in the performance of the public transit service. A good frequency design plays a key role in not only satisfying the daily travel demand, but also lowering the passenger travel time and operating costs. Therefore, the transit frequency setting has received much attention in the literature. So for most of the model of the, most of the model for transit network frequency setting program focus on a single period frequency design, which is only determined by the demand levels and distribution of the traffic demand during the peak period. And also for most existing the multi-period TNFSP model, they did not consider a general transit network, or they consider the adjustable fit sizes of the whole network in different periods, but they only determine the different frequency setting in various periods, and they ignore the data that affect the frequencies of the next period. Just like that should also will reduce the fit sizes of some other routes. As a result, some route frequency settings for the next period derived from their model may not be achieved in reality. So the impact of the data did not receive sufficient attention in the executive study of the multi-period TNS FPS. What's more, the existing models mostly assume that the route frequency in two opposite directions are equal and do not account for the implication of the imbalance and asymmetric demand patterns in different directions. To sum up, multi-period TNFSP model for the general transit network with asymmetric demand concerning the adjustable precises for all routes and that have trips over periods has not been defined yet. So we also noticed that the bus operator serving the Tinshui a suburban residential area in Hong Kong is also facing the same issue. Most of the residents in Tinshui work in the urban area of Hong Kong. The bus service is the main commuting mode for the Tinshui residents. However, compared with the stable and relatively balanced ridership bound from and for the Tinshui in off-peak hours, passenger travel demand has significant directionally characteristic during the peak hours. However, the traditional symmetric design still cannot fully meet the symmetric demand pattern. So the operator hope to adjust the current design for the developed network to adapt to the passenger demand variation and improve their operating profit. Especially like in the peak hours, the route frequency should increase in the direction with high demand, while that in the road demand direction should decrease to allocate more buses to the high demand directions. So as a result, the operators propose a strategy. There are two classes of buses. Class A will serve both two directions, while Class B only serve one direction with the high travel demand in each route. So, however, no study propose a methodology to model and examine this strategy in the whole network for a day. But based on their feedback, this strategy not only attract more passengers and improve the passenger travel time, also increase their operating profit to a certain extent. So the applicability of this proposed strategy should be further investigated. So we try to bridge this methodology gap. So more details, the fixed size of each period can also be adjusted by the introduction of the diatribe between the terminals of routes over periods. Moreover, they will use different frequency setting during the different periods of their operating hours. Different from the existing model, the route frequencies of these two classes of buses are adjustable in each period. Also, the diatribe between the bus depots and terminals or between terminals of different routes over the operating periods are also considered in the model formulation. The study problem is to determine which direction of each route should be served by Class B buses and the optimal frequencies for both Class A and Class B buses of each route in different periods, and the diatribe between periods. So here are some key notation, just what I mentioned before, just like the frequency of each classes buses and the diatribe. Also, we apply some classic assumption in this study. The passenger go to their destination using the minimal transfer. We did not limit the transfer number. The passenger board the first arrived bus in the set of the attractive bus loops, and the demand is distributed based on the relative frequency of attractive bus loops. And also the passenger demand of each OD pair is elastic with respect to the generalized travel costs. And also the total diatribe and over time of bus is 1 hour, which means a bus serving one route in the previous period cannot serve any other route until the end of the current period if it takes a diatribe in the current period. So here's the basic framework. Our objective is to maximize the operating profit or the social welfare. And also here's some constraint about the fixed size equation for different periods, and also the fixed size limit. And also here are some frequency definition for the Class A frequency, Class B frequency, and the frequency for two opposite directions, and also some frequency limit. We can find that the constraint and the objective functions are some constraint, and the objective function is all nonlinear. So the decision variables contains both integer and continuous variables. So the formulation is a mixed integer non-convex nonlinear program. As this program is difficult to solve, a heuristic and or meter heuristic is required to solve this problem in the large network. So in the following, we will propose EABC enhanced artificial being canonic. So since the time is limited, we will not show the algorithm too much. To sum up, we embed 3 sub-algorithms in the EABC. So the algorithm 2 is the setting changing period identification. So we do not hold the frequent change in the different periods. We only change the setting change, the frequency setting only when the demand patterns is changed. So also we try the algorithm 3 to restrict the initialization. So we want to make sure that our initial solution is all feasible. Also, we use the reapply the neighborhood search algorithm 4 based on our problem to ensure our solution quality to input there. For the solutions representation, since as the main constraint of our problem are the precise constraint, the frequency setting problem can be reformulated into the problem of the allocating a limited number of buses of route and some data and all data in each route between each period. So we reformulate into the problem in the algorithm. Also, we found that with the EABC converges more quickly and can produce more effective solution with better objective values than the modified generative algorithm MGA. MGA is our benchmark. So also here are some interesting results. No matter what objective we choose, just like the operating profit or the social welfare, all vehicles should be put into the operation during the peak period. Although the main difference between these two objectives is the number of non-service buses during the off-peak hour. For example, just like if we choose the social welfare, we may decrease the fixed size for some route during the off-peak hour. Also, we compare the traditional symmetric design throughout the day, and we also find that proposed design performs better than the traditional design in all-day operation to ensure the different degrees of improvement in both peak and off-peak hours. So also we found that as the minimum frequency decrease or the demand level increase, the proposed design provides more significant benefit to passenger and the operator. So that's the end of my page. Thank you.
Thank you very much. This is a little bit out of my expertise, so it's going to be a very basic question. But I want to ask, how do like bus operators in Hong Kong actually do the assignment at the moment? Because I would assume that maybe they base it on
Yeah.
their experience, so they have been doing this for a long time, so on their experience. And whether do you think this kind of like just heuristics based on experience are working for them? Because I would assume they would not like to lose some profits, right? So
Yeah. Since this area is a classical residential area, so most of the people they will just work in the area, the suburban area, the urban area of the Hong Kong. So we find that they have the significant directionally characteristic during the peak hours, different from the off-peak hours. So in this for this operator, they hope to address not for the all operator, since different operator may different. So we only focus on this study area. So they find that use this operation strategy can make them receive high operating profits. So, but we found that no study to examine this strategy. So we want to, and we're investigating, and also just like enlarge to, and also give them to the a more optimized strategy, the dispatching, just this dispatching assignment to them to make their strategy more better, just like that. Yeah.
okay, so do you think they can? So are you in touch with the operator so they can actually test run your algorithm? Is that what you said?
Sorry.
So I want to understand, like, did you said that are you actually in talks with the operator to actually have them test your proposed algorithm or?
Yeah, they will they will also talk to talk with us, and also we found that the passenger can read the frequency setting easily, not for frequent changes. So that they think this is okay. So
Okay. Thank you very much. I don't see any other questions on the chat box, so I would like to wrap it up here. Thank you very much.
thank you.
And then I would like to move on to the next presenter, that it's gonna be Mingxuan Chen from talking about the loading strategy for bike repositioning problems with e-bikes and conventional bikes. So whenever you are ready.
Testing. Can you hear me?
Can the volume is a bit low. Can you?
Testing. Can you hear me now?
It's a little bit low. Can you talk? Can you?
Testing.
Good.
Okay, thank you. So thank you, Professor Parati. Good morning, afternoon, and evening. This is Mingxuan from the University of Hong Kong, and I'm also from the research group of Professor Jintao. Today, I'm going to talk about a loading strategy for bike repositioning problem with e-bikes and conventional bikes. Okay, so bike sharing systems have been implemented worldwide. So in such a systems, users are enabled to rent a bike at a station, ride it all the way to the destination, and return a bike at another station. Bike sharing has been regarded as a healthy, entertaining, and environmental friendly mode of transport. Well, at the end of the day, due to the user activities, some stations may become in surplus or deficit in terms of bikes. This will result in failed user requests. For example, here, the user cannot rent a bike at an empty station. So that's where bike repositioning comes in. The purpose of bike repositioning is to rebalance the number of bikes at each station. So a typical way is to hire a truck and transport a bike from, for example, station B and all the way to station A. In the back repositioning problem, it includes a routing problem, that is which stations to visit and what is the order of the visits. And also there is a loading and unloading subproblem, that is how many bikes should be loaded and unloaded at each station. And one of the challenges now is that some operators have been offering both e-bikes and conventional bikes in their system. For example, in this picture, the circled bike is a shared e-bike. And there are pros and cons for shared e-bikes and conventional bikes. For shared e-bikes, they are normally easier to ride and faster, but normally they will be charged at a higher rental rate. Well, for conventional bikes, the rental rate could be lower, but it is purely driven by human power. And also in terms of speed, it is in general slower. And the challenge in the loading strategy is that the vehicle capacity is limited. So how to allocate the limited vehicle capacity between two types of different bikes? So here's the problem description for this bike repositioning problem. Each vehicle departs from the depot at most once. Each station is visited by at most one vehicle. And the vehicles do not carry any load when it leaves or reaching at the depot, and the vehicle capacity cannot be exceeded. E-bikes and conventional bikes are considered to have separated demands, and the objective is to minimize the weighted sum of the total deficiencies of e-bikes and conventional bikes and the total travel and loading and unloading time. So here's the model for the back repositioning problem. So the first two terms are the weighted total deficiencies in e-bike and conventional bikes, and the third term is the sum of the travel time and loading and unloading time. In terms of constraints, the total deficiency is defined by the sum of the deficiency minus the bikes unloaded at a station, and also at each station, the total number of loading or unloading are bounded by the surplus or deficit at a station. So with the model given in the previous slide, the loading and unloading subproblem can be extracted from it by assuming that the route is already given. So once the route is already fixed, the remaining task is to find out the loading and unloading quantities at each station. Again, the first two terms are the weighted deficiencies for e-bikes and conventional bikes, and the third term now only contain the loading and unloading time. So this is a set for all the stations on the route. And again, the loading and unloading quantities are bounded by the surplus and the deficit at a station. And because the D terms refers to deficit at a station, they are parameters. Sorry. So they can be removed from the objective. By rearranging the objective, we get this. So because the decision variable R, which refers to the loading quantities of e-bikes and conventional bikes, they are non-negative. So if the parameter in the brackets are also non-negative, then there will be just no benefit to do any relocation. By assuming that the parameters in the brackets are smaller than 0, so two specific cases are considered. Firstly, the unit penalty for e-bike is far larger than that of a conventional bike. And the second case is that the unit penalty for e-bike is just slightly larger than the conventional bike. So actually for each case, there is a tailor-made algorithm, but due to the time constraint today, algorithm 1 will be the focus. Let's consider this example. So supposing we have a route with 8 stations, and the surplus and deficit of e-bikes and conventional bikes are shown in the table above. So the blue values are the surplus and the red values are the deficit. A simple way is just to consider the loading and unloading in a forward greedy method. So forward means that the loading and unloading quantities are confirmed from the beginning of the route, and greedy means that we just basically load or unload as many as possible. So this will result in a loading and unloading quantities like this. And after having this, we can also calculate how many e-bikes and conventional bikes are loaded on the vehicle when it travels from a station to another. For example, after loading 19 e-bikes at station 1, there will be 19 e-bikes on the vehicle when it travels from station 1 to station 2. However, there are two problems can be observed here. Firstly, there are some e-bikes loaded, but they are not unloaded at any other stations. This violates one of the problem descriptions. And also, previously, we just assumed that the vehicle has infinity capacity. But just suppose we have a capacitated vehicle. So it has a it has a maximum capacity. Then at these locations, the vehicle capacity is exceeded. So again, this reminds us that one of the challenges is that how to allocate the limited space between two types of different bikes. So in this paper published in 2018, they considered the loading and unloading strategy for a single type of bike. And the idea is that the bike should only be loaded if they can be unloaded at the following stations. So following their idea, if we consider the loading quantities for e-bikes, so for example, at station 3, the outstanding deficit at the following stations from 5 to 8 is 13, and the deficit at station 4 is 6. At the same time, the current load of e-bikes on the vehicle is 7. So instead of loading all 14 surplus e-bikes at station 3, loading just 12 will be enough to fill the deficit at the following stations. So by doing this, there will be no e-bikes loaded but not unloaded at another station. And if we just consider e-bikes, the vehicle capacity is not exceeded as well. So using the similar idea, let's consider the loading and unloading strategy for both e-bikes and conventional bikes. Because in algorithm 1, e-bikes are prioritized because it has a far larger unit penalty. So here we consider the loading quantity of e-bikes first from backward, and then at the same time for the unloading quantity, we just assume that all the deficit can be filled. And the unloading quantity will only be figured out after the loading quantities are calculated. All right, so the gray value means that we just assume that the deficit can be filled by loading e-bikes there. So when we consider the loading quantity at station 3, the current outstanding deficit at station 3 is 19. The calculation process is here, and the station surplus here for e-bike is 14. So taking the minimum value of these two, 14 e-bikes are loaded at station 3. And for station 2, we just assume 12 can be unloaded. And for station 1, the outstanding deficit here is 17, while the station surplus is 19. By taking the minimum of these two, loading only 17 e-bikes will be enough to fill the deficit at the following stations. So after having the loading quantities, the unloading quantities, together with the loading of e-bikes on the vehicle along the route can be calculated. And then we proceed to consider the conventional bikes. So for example, at station 7, the surplus of conventional bike is 5, and the deficit at station 8 is 15. So we can just load 5 conventional bike at station 7. However, when it comes to station 6, so now the outstanding deficit is 10, and the station surplus is 5. But because we already know that there will be 16 e-bikes on the vehicle when it travels from station 6 to station 7, which means that at most 4 conventional bikes can be loaded at this station. And similarly for station 4, the outstanding deficit here is 14, the station surplus is 13. But because there will be 13 e-bikes on the vehicle when it travels from station 4 to station 5, so at most 7 can be loaded at this station. So also similarly at station 2, although there are like 16 surplus conventional bike at the station, at most 15 can be loaded. So after having the loading quantities, the unloading quantities, the red numbers, and the loading of conventional bikes on the vehicle along the route can be calculated. Okay, so if we consider the loading the e-bikes handled with the previous slide, the difference is that the loading quantity of e-bikes was considered from the beginning of the route on the previous slide. So the drawback is that it cannot minimize the loading of e-bikes on the vehicle along the route. For example, in the circled area, if we follow the loading quantity of e-bikes on the previous slide, there will be 7 e-bikes on the vehicle when it travels from 2 to 3, which means that it will be impossible for us to load 15 conventional bikes at station 2 because of the vehicle capacity. So here, if we check the vehicle loading at the critical points, we can find that the vehicle capacity is not violated. And here, the algorithm 1 completes with no e-bike deficit, and the conventional bike deficit is equal to 8. So the previously mentioned algorithm is just to solve the loading and unloading subproblem. So for solving the whole problem, hybrid genetic search adapted from this paper used for like capacitative vehicle routing problem is used in this problem. So the loading and unloading algorithm is only called when we need to solve the loading and unloading subproblem. Okay, so in terms of numerical experiments, if we compare the hybrid genetic search with surplus, with Cplex, for those instances that can be solved optimal by Cplex within 2 hours, so hybrid genetic search can also get the same value. And for those Cplex cannot solve to optimal in 2 hours, hybrid genetic search can either get the same value or have a better result. And also in terms of computational time, the hybrid genetic search can save lots of computational time compared to Cplex. And actually, the loading and unloading subproblem can also be transformed and solved by linear programming. So in this slide, the efficiency of the two solution method, algorithm 1 and linear programming, is compared. So here for these instances, they can get the same result, but in terms of computational time, the hybrid genetic search with algorithm 1 embedded can save lots of computational time compared with that embedded with linear programming. Well, in summary, a bike repositioning problem with e-bikes and conventional bikes is considered. A tailor-made algorithm is designed for a special case for the loading and unloading problem. And this algorithm prioritizes e-bike, figures out the loading quantities from backward, and then finds the unloading quantities accordingly. This algorithm is also found more efficient than linear programming in solving the loading and unloading subproblem. And here are the references used in the slides, and thank you very much for listening.
Thank you very much for that presentation. It's gonna be a similar question to the previous presenter as well, but I'm curious about how the actually operators, how do they do it at the moment?
Okay, so actually, I don't have any like local cases because like bike sharing is not that popular in Hong Kong. But for example, in the mainland, I think they should be able to use some of the maybe heuristic ways to do the loading, do the bike repositioning, because you can see, so for example, in this picture, they have the lorry going to a station and loading the bikes here and loading some bikes there. It may not fully apply the very detailed method here. Maybe I think they are using some simpler ways to handle it in terms of the bike repositioning in the real world.
Okay, so there's no like industry standard regarding like what will be the best algorithm or the most commonly implemented algorithm to deal with this rebalancing thing?
Currently, I think for this research only, I think it's just for developing the algorithm for a specific problem. But whether or not it is efficient in the real world, it still need to do some real world tests to do it. I'm not sure about the actual results of this.
Okay, thank you. There's a question from Mehmet. So he says that he asked whether your model considers charging at stations, or does it have constraints regarding the charging duration?
Oh, thank you for the question. Actually, charging is also an important point for e-bikes. In this study, actually, e-bike is just considered as another type of bike with a higher rental rate, and they occupy the same space as a conventional bike on the vehicle. So in this study, the charging problem for e-bikes is considered as a separate problem. So we don't consider charging here. So in terms of real-world application, this can be explained 2 ways. So firstly, as I said, the charging for e-bikes can be considered as a separate problem. So maybe in the daytime, the operator swap the batteries for the e-bikes, and then the repositioning of e-bikes is considered as a separate problem. So as in this study. And another way is that apart from swapping batteries, e-bikes can also be charged at some charging stations. And the charging stations will usually be designated for e-bikes, but not conventional bikes at the stations. So if there are charging stations in the system, so in a static back repositioning context, the e-bikes can just be unloaded, whether or not it is charged or uncharged. They can be unloaded at a charging station and plugged in, and then after the nighttime, so in the next morning, it will be charged and be able to use for the and be able to serve the users in the system. So that's a good question. So actually, indeed, charging is an important issue for e-bikes, and there have been lots of research recently regarding the e-bike charging problems, especially in the e-bike sharing systems. So here we didn't consider charging in this study.
Thank you very much. It seems there are no more questions in the chat, so I would like to wrap it up here. Thank you. And then I would like to move on to our next presenter, Xuan He, talking about using mobile phone big data and street view images to explore the mismatch between walkability and walking behavior. So whenever you're ready.
Yes. Dear professors and friends, good morning. I'm Shen He. I just completed my PhD at the Chinese University of Hong Kong. My supervisor is Professor Sylvia He. It's a great honor to introduce our research here. The topic is using mobile phone big data and street view images to explore the mismatch between walkability and the walking behavior. The research has been published in Transportation Research Part A, and you're welcome to read and cite our paper. These two pictures show different streets, and I would like to ask a question. Which street would you prefer to walk along? I believe most of us would prefer walk along the right street with street greenery, street lights, and sidewalks. However, the left street has no sidewalks and no street lights. Obviously, the built environment on the right is more friendly for the pedestrians. And walkability is defined as a measure of how the built environment is pedestrian friendly. Walking has substantial benefits to people's health and can reduce carbon emissions. A walkable city can promote the healthy city development. So in order to promote more citizens to walk, it's important for us to understand the relationship between walkability and walking behavior. After reviewing the literature, I identified several research gaps. And first, the typical walkability frameworks, such as the 3D and 5D frameworks, are developed from the perspective of urban form and based on random utility series. They assume pedestrians make decisions based on the maximum utility, the shorter time or shorter distance. But in reality, pedestrians may prefer walking on a safer or more attractive areas or routes, rather than shorter times or shorter distance. Obviously, these typical frameworks overlook some important pedestrian needs. And most of them consist of meso-scale built environment features at neighborhood level, like land use means street connectivity. And they overlook some micro-scale features at street level, such as trees, street lights, and sidewalks. Even they have a greater association with walking activity. Regarding the walking behavior, most studies collect walking behavior through conventional approaches, such as surveys and portable devices, but these methods are costly and limited to a small spatial temporal coverage. And big data approach, such as mobile phone big data, receive little attention in walking behavior literature. More importantly, in the existing big data and mobile phone big data study, the validation part is commonly unclear. And that is a point because further discussion on big data study without verification is probably meaningless. The last point is that for the relationship between walkability and walking behavior, most studies explore the general knowledge and highlight the positive or negative effects, and then they propose the city uniform strategies. But the city uniform strategy may not fit all regions in the city. And the mismatch areas with high walking trips but low walkability receive little attention, And identifying this mismatch area is very important because they can prioritize strategies and improve policy efficiency. And this study aims to address 3 research questions: how to measure walkability from the perspective of pedestrian needs, and how to extract walking behavior from mobile phone big data and validate the methodology, how to identify the mismatch areas between walkability and the walking behavior. The study area in Shenzhen is one of the most developed large cities in China and undergoing rapid urbanization in recent decades. Shenzhen is also a pioneer city. The study of it might inspire other Chinese cities. And here are 10 districts in Shenzhen. Generally, Nanshan, Futian, Luohu are urban area, and the other 7 districts are suburban area. And the suburban divided into 2 parts: inner suburban in orange and outer suburban in gray. And the study unit, the neighbor scale is 1 kilometer gray in our research. Walking behavior are extracted from mobile phone data, and I focus on collective walking behavior. The variable is the number of walking trips in the neighborhood. And through this process, walking trips are extracted from 6 months of mobile phone data. The data is cellular tower-based data collected from CMCC company, the largest telecommunication company in mainland China. And walking trips are extracted through rule-based heuristic method. I totally collect over 174 million walking trips in Shenzhen. I collect some ground truth GPS data to validate the walking trip extraction method. I recruit volunteers to collect their GPS data for 2 weeks through the mobile app. At the same time, they report their trips and transport mode. And then I convert the GPS data to the cellular tower-based data and use the DCM method to extract the walking trips from the data. And based on confusion matrix, I calculate the accuracy rate of the walking trip extraction method. And it's more reliable than previous studies that validate their methods with official model share or aggregate data. Based on social psychological theories, I built walkability frameworks from 4 pedestrian needs: safety, convenience, continuity, and attractiveness. And all the variables extract from open data, such as street view images, social media data, UI data, government open data, and GIS data. And the framework also integrates meso scale and micro scale environment features. And micro scale features is the 3 features extract from street view images. And this figure shows how to extract 3 features from the images. And first, I generate the sampling points along the Shenzhen Road network, and then download 3 view images in 4 directions at each point. And I use semantic segmentation to extract the target features from the images. And here is an example. The pixel with different color represents different 3 features. For example, the blue area represents sky, and green area represents greenery. And I tested in semantic segmentation model for each target 3 features to find the model with best performance. And I finally selected 3 models and training under 2 open data sets. After collecting the walking trips and measuring walkability, I used geospatial analysis to explore the spatial the match and mismatch area between walkability and the walking behavior. And I also used GWPR to explore the spatial varying effects of walkability on walking behavior. This figure shows the match and mismatch area between walkability and walking trips. And I focus on, and I would like to highlight the low walkability but high walking trip cluster in red in this figure. And most of these areas located in the fringe part of the subcenter in the city and in the urban villages. I'm not sure if everyone familiar with the urban village in China. It's an informal housing type and provide cheap and high density housing for the low income people. It's quite popular in the large cities in China. And even the urban villages have high density walking demand, but they serve by pretty poor walking environment in the city. And the result of GWPR reveals the spatial varying effect of walkability on walking behavior. And first, the positive effect of walkability is strong in the fringe part of urban areas and in the inner suburbs. In terms of the 4 subdimensions, the positive effect of safety is strong in the suburban areas. and the positive effects of convenience is stronger in the outer suburb. The positive effect of convenience is greater in the western part of the city. And the positive effect of attractiveness is clustered in central and western part of the city. Because the resources are limited, so for the 4 cluster type, the government should prioritize their resources to intervene the built environment in the low walkability but high walking trip cluster. Because these areas have high density walking trips but served by pretty low walkability, so they need more priority. And second, I propose the intervention strategy for each cluster type. For example, the strategy for the low-high cluster is enhancement, and the strategy for the high-low cluster is encouragement. That means government should promote the health benefits and the walkable environment in this cluster to encourage more citizens to walk there. I also identified the priority areas for each cluster type. Because the resource is limited, so government can prioritize their intervention in the cluster located in these priority areas. They may get better outcome. For the policy insight part, I'd like to share 2 photos I took during my field trip last summer in Shenzhen. Actually, in the early urban planning in Shenzhen, there was a tendency to marginalize active transportation because they believe walking and cycling is a symbol of being backward. So they narrowed the sidewalks or removed the bicycle lanes to widen the traffic lanes. As a result, pedestrians like this boy has to walk super carefully on the traffic lanes and endanger the cyclists riding there without bicycle lanes. And in conclusion, our study explored the mismatch between walkability and walking behavior in Shenzhen by using mobile phone big data and real images. And we identified the mismatch areas and explored the spatial varying effects of walkability on walking behavior. And based on the finding, we proposed some prioritized and contextualized built environment intervention strategies and policy implication. We also shed light on the fact that the city-wide uniform strategy may not fit all regions in the city, and urban planners should perform strategic intervention based on the spatial patterns to foster walkable and healthy cities. Thank you.
Thank you very much. Can you show them the mismatch map? Where you have the high, 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 low, low, high.
Yes. Here.
Yes. So there's 2 things that I'm curious about. First of all, like, what is the population? How much of the population lives in the high, high area, in the high, low area, in the low, high area, and in the low, low area? Because I think when you're thinking about a policy intervention, like, also how many people are you actually addressing, right?
That is the high, low, and low, high is related to the walkability and the walking trips, and the walking trip, the number of walking trips may be related to the population, but here we just focus on these 2 variables, and maybe the like the area with more walking trips is high density area is also quite common.
But not related to density, but in general, like when you think about, like, if I ask you what percentage of sorry, this is I forgot the city, but what percentage of this city, Shenzhen, sorry, what percent of this city lives in the high area, for example? 20%, 30%?
Oh, you mean the I didn't count the number of like the population in the high areas, but it's quite common for the cities in China that more people living in the in the subcenter or the CBD areas. Or it's quite common like by more people living in the urban areas and the suburban subcenter in the city.
Okay, I think the point of my question is that perhaps when you're thinking about, like, okay, and what is an effective policy intervention, we want to focus on how many people are actually targeting with that intervention, right? And since the interventions that you suggested, like encouragement or enhancement, are related to the clusters, it might be interesting to calculate the amount of people targeted in each segment.
Yes. Yes, yes, thank you for your question. And yes, but here I focus on like the walking demand, the number of walking trips, but population is also quite interesting. And in my the other study, and I focus on like walkability and population, but it's in other cities in Dubai, it's not in China. And
Okay.
that in that study, I focus like to see that the mismatch between walkability and population. And also I have some interesting findings, like the high low walkability but high population areas are in the low income neighborhoods in Dubai, like that
Okay.
during my visit. Yeah.
And then one other thing that I'm curious is like when you look at the gray area, it seems to cover a large area, similar related to my previous question. The non-significant clusters, it's actually a large area. So what policies do we address in these cases?
It means, yes, I understand. The result is it will create some no significance areas, but I think the policy part is like is in these slides. Is the government should prioritize the intervention because the resources are usually limited, and the government don't know where they should prioritize the intervention. And the low walkability but high walking trip cluster or areas, they need more priorities because these areas have high walking demand but serve a pretty low, very poor building environment there.
Okay, but again, I think it goes back to the question, like if a lot of people live in the gray areas, or if most people live in the gray areas, then we need to think about what to do there too, right? But again, this is a comment, like maybe for further analysis. There's another question by Yikan. So it says, have you considered the dynamic change on these different clusters? It's nature that the boundary areas will evolve. So it's natural that the boundary areas will evolve. So how the corresponding strategies align to this dynamic change? I mean, Yikan, maybe you can unmute yourself and explain.
Oh yeah, great. So it's let's go back to the maps. Like we have different 4 clusters, right?
Yeah.
But yeah, so I can see this kind of I mean the boundary areas between different clusters may not be that arbitrary. So it may involve like the area could be low high area after a while. So we will change the corresponding strategies because of this dynamic change.
Sorry, I didn't catch you.
Yeah. So it's so have you considered the evolvement of the different clusters? Yeah.
Yeah. Yes. That point I also highlight in the paper because the low high cluster, low walkability but high walking cluster, they're located in the fringe part of the subcenter. They may be related to the involvement, like at the very beginning, the subcenter is walkable and is very friendly environment for the pedestrian, but the boundary of the subcenter become larger and larger. There are more population in the subcenter, and then the high walking trip areas is larger than the walkable areas, so create the low high cluster in the fringe part of the subcenter. Am I clear?
Okay. Yeah, that makes sense to me. Yeah, great. Thank you.
Very good. Thank you.
Okay, thank you very much. So if there are no more questions, I would like to wrap it up here. And there's a question there. I found that the low high clusters, most of them dotted around fringe areas of CBD and subcenters, but there is very mixed in the middle part.
Yes, because in the middle part, some of them is in the urban villages. In the middle part means in within the subcenter or CBD, there are urban villages in the city, like Chen. So they in the middle of the part. Am I clear? Because urban villages is they have high density or high population in these housing areas, but they but usually it's coded from the formal urban planning. So they have a high walking demand. They serve a pretty cool environment there.
Okay. Does that answer your
Thank you.
question? Great. Okay, so just about time. Let's move to the fourth presentation. The fifth presentation is e-bus ridership satisfaction willingness to pay by Timothy Wong. So Timothy, whenever you're ready.
Hi. Okay, let me
Perfect.
get this screen shared. This here. Hold on, let me. Okay, great. You can hopefully see my slides now, right?
Yes.
Great. Okay. Right. Hi, everyone. My name is Tim, and I am from the National University of Singapore. Thank you very much for being here to attend this presentation on my work that I've done with my colleague here at NUS, Alberto Salvo. We're both from the economic department here. So the title of the presentation is Electric Bus Ridership, Satisfaction, and Willingness to Pay. Yeah, okay, so let's get into it. Sorry, for some reason here now I'm having, okay, great. The slides are moving. Okay, right, so electrification of urban buses, which includes buses for public transport and school buses. That's been proposed as a approach to reduce air pollution and meet climate mitigation targets. In 2021, the sale of electric buses grew quite rapidly, 40% over the previous year. But the base is still quite low here. Only about 4% of the global bus fleet has been electrified. So it's an important emerging topic to look at, right? Most studies that look at the effects of bus electrification, they assume that demand remains unchanged. So they look a lot at the supply side and how things change because of the change in energy source, but you assume that riders sort of behave in the same way as they've always done. So in this paper, what we do is we test this assumption that commuters are indifferent between electric and diesel buses. And we do this because there are amenities worth capturing from these electric buses, right? There are lower noise levels and also less local particulate matter from the exhaust pipes, right? And we believe that this could be quite important because if you are a public transport user, waiting at your bus stop or your bus bay can be the moment of peak exposure to air toxins when a bus stops and then leaves, and then you get all of the fumes that come from the tailpipe. The context that we are looking at here is Singapore, because that's the city that we are in. And because Singapore's Transit Authority, known as the Land Transport Authority, began electrifying buses beginning in April 2020. So here we have a photo of the electric buses that were introduced. They are very similar to the diesel buses within the system. They are the same color. They look more or less the same, but they have a few distinctions. The first being that when you board the bus, there's this very small sticker here that says that the bus is an eco bus. And then if you board a double-decker bus, at the back of the bus, because there is space, they put a big sticker that says, you can read it here, eco-friendly electric bus, 100% cleaner energy. So there is some distinction between a diesel bus, but for the most part, the colors and the look are the same. All right. During the period of our study, which is April 2020 until for about a year, there are only 60 electric buses that get deployed. This is the beginning of the conversion of the fleet for Singapore, relative to a fleet of 4,000 buses. So this is a drop in the ocean. There are a small handful, I want to say maybe fewer than 50 hybrid buses within the fleet as well. So I'll start off by just giving you a quick summary of our findings. We look at 3 data sources. The first is ridership data from LTA, from the Transit Authority. This is data on how people tapping in and out of the buses, riding the actual buses. Then we conduct 2 surveys. The first I call an intercept survey. That's where here what we do is we go to bus stops and we interview or survey commuters when they are getting off the bus. And then the third is we run stated choice experiments with households. So that I call a household survey. And I'll give you more details on that in just 2 slides here. So our findings are first from the ridership data. We find that there is in the specification that we are most comfortable with, there is an 8% increase in ridership on bus lines when a line becomes fully electric. From our intercept survey, what we find is that commuters who step off the electric bus, they are unable to identify whether the bus is electric or diesel. So they are not attentive to the powertrain of the bus. But that said, when you ask them about their satisfaction with the noise, when they step off an electric bus, they do say, oh, they are more happy with the noise levels when they were on the bus. And then finally, in our household survey, what we did is we gave our participants 2 choice experiments. In the first choice experiment, they have to choose between the powertrain of a bus. So either the bus is an electric bus or a diesel bus. And at the same time, there are different travel times associated with these buses. So they make that trade-off. And then in the second choice experiment, they have to choose between an express bus and a regular bus. So that's a time trade-off. But of course, the express bus is going to be more expensive. And when we put these 2 choice experiments together, we can estimate a willingness to pay for an electric bus ride. And from that, we get a number of 8.5 US cents per ride. So that's how much more people are willing to pay to sit on an electric bus instead of on a diesel bus. That aggregates up to $122 million more per year, or $20 more per resident per year. Okay, so I'll start here by giving you more details on this ridership data that we have, how we come up with this 8% increase in ridership. So what we did is we asked the LTA for data on 15 of their busiest bus lines that were in our intercept survey, where we were surveying people at the bus stops. So from the intercept survey locations, we pulled the 15 busiest lines. 7 of those lines were lines that were partially electrified, and the remaining 8 were fully diesel across the entire sample period. Now, which lines received electric buses? That was a decision that LTA made based on supply considerations. Basically, because it's early in the introduction of electric buses, they were trying to test out these buses on different types of lines. So, for example, they had some electric buses on longer trunk routes that take you from one end of the island to the other end of the island. And they also had some that they put on short feeder loops that take you from an MRT station round to a small neighborhood nearby and then back to the MRT station. Just trying to observe the performance of buses in various types of conditions. Each observation that we have here is a bus ride that's marked by the time that they get on the bus and the bus stop at which they tap on. And we have a total of 104 million rides from the 1st of July 2019 to the 30th of June 2020. Pictures paint 1,000 words. So here's a graph of monthly ridership. You'll see here that for the 15 lines that are in our sample, so you'll see that there are these changes across time, and then it's a sudden dip in April 2020. Most of you will remember that's when COVID was at its starting to rear its head. And so in Singapore, we had mobility restrictions between April and July of 2020. People had to stay at home. Ridership picks back up again. And then there is a second wave. We have mobility restrictions at the tail end of our sample again. And so these vertical lines indicate to you those periods of time. The second graph that I want to show you is the rate of electrification for the 7 lines that we have in our sample. As I said earlier, the electrification begins in April 2020. And so you'll see a rise in the percentage of buses on particular lines that are electrified in April of 2020. But the important thing to point out here is that electrification is staggered. So you have, for example, 944 is this line that gets 80% of its buses, 85, almost 90% of its buses are electrified for a long period of time, and then it basically loses electrification towards the end of our sample. But there are other bus lines that remain diesel lines until later, until August or September. Then you see this one right here is 354, I think. Right? 354 becomes quite electrified. There are also different rates of electrification. 944 and 354 are very highly electrified. But if you look at this one, 983, it has about 10% of its buses are electrified. So we have all of this variation going on during our sample period. Right, okay, so then getting to the results. First thing that I have here is what we do is we aggregate up all of these rides to the level of our bus lines and week. So this is the observation here is the number of rides on a particular bus line in 1 week, okay? And then this is a standard fixed effects or difference in difference regression where we control for the bus line and we control for time for the week. And if I just put in a variable that captures the proportion of buses that are electrified on that line, you'll see that there is a 14% increase in ridership when the line is fully electric, right? In second, third, and the fourth columns, we control here for a few things. The proportion of buses that are double-decker. This is to control for capacity, right, of seats on the line, and also for the age of the bus, because presumably new buses people might like more. So we control for that as well. When we control for those things at the same time, it falls to 12%. And then this last column here, we sort of break up the effect based on whether the line was highly electrified or lowly electrified. But here we're using dummy variables rather than proportions. And there you see that you get stronger effects for 944, 354, and 990. The more electrified lines, that's where these results are coming through. Okay, but we're not yet at our headline result. The previous slide, those numbers are higher than what we think we should go with. So what we've done here in this next slide is we've tried to control for changes in demand that would come from changes in the housing stock. So a big thing about Singapore, a very centrally planned city, is that housing neighborhoods and housing blocks can come up in large quantities all at the same time when the government decides to open a new neighborhood. And so what we do here is we identify a certain area close to the bus stops, and we check how many increases or decreases in dwellings there are around those bus stops, and we remove those from our sample. So that we don't have here that a confounding factor where this increase in ridership we think is coming from electrification, but really is coming from the fact that there are more people now living in the neighborhood. So when we exclude those bus stops, right, exclude the rides that are coming to those bus stops, we get that our effect then falls, and it falls to about 8%, depending on how you define the observations that we remove from our sample. And that's the headline result here. We're happy with that ridership. Once you remove this exogenous shifts in demand from new people moving into the neighborhood, 8% increase in ridership. A few other things that we find that I won't show you the tables for is that ridership increases with both the electrification intensity. So the more electrified the line is, the more ridership there is. And also the longer a line is electrified, the ridership increases. And that to us suggests that commuters here are learning and responding as they become more aware to these changes happening on their lines. And then there's just a list here of a couple of other confounding factors we were concerned about. And so we ran some robustness checks and our results hold to them. Even if we drop 944, which was the highly electrified line, our effect is still 0.5 to 0.7%. Okay, the next thing I want to talk about is this intercept survey. So the other thing that we did is we went to bus stops and we talked to people, asked them a very quick question about the bus that they rode when they get off the bus. So we covered here 4 neighborhoods within Singapore, all very quiet, and most, on average, in the median number of buses serving each of these bus stops is just 2. There are 22 bus stops, 31 lines that are covered, and we interviewed almost 1,300 people getting off both diesel and electric buses between December 2020 and April 2021. This is the survey. We asked them 2 questions, or two categories of questions. The first is, how satisfied are you with noise, fumes, smoothness, and speed of your ride? You can answer satisfied, neutral, or not satisfied. And then we asked them to describe the bus that they just took. So tell us the age of the bus. Is it new, okay, normal, old, or they don't know? Engine type, is it diesel, electric, hybrid, something else, or they don't know? And then the number of decks, is it a single deck bus, a double deck bus, and so on. So based on that, we have some results too. We then went and got the actual descriptions of the buses that these commuters rode from LTA. So we know, regardless of what they said, we know whether the bus is diesel or electric. We know how old the bus is, all of those things. And we could then verify whether these commuters were aware of whether the bus they're getting off is electric or diesel. And maybe not too much surprise, only 34% of people who step off a diesel bus can correctly identify their bus as diesel. And only 24% of people who step off a electric bus can identify their bus as electric. The proportion choosing don't know is high, 54 and 55% respectively. But that also suggests that the electric bus people more of them are getting it wrong by saying it's diesel or hybrid, right? Relative to the diesel people, where 34% of them are getting it right. Right, so one thing we thought, maybe it's difficult for commuters who get off partially electrified lines to tell you whether the bus is electric or diesel, because sometimes it's electric, sometimes it's diesel, and they're not always paying attention. So we thought, let's limit ourselves to the sample of commuters who are only on these bus lines that are fully diesel. So there's no changes here going on. Every bus they get off is a diesel bus. Can they then tell us that the bus is diesel? The answer is no, right? Still about 36% of them correctly identify their bus being diesel, and 54% identify it as say that they don't know. So you don't do any better on fully diesel lines. Right, speaking to this question of don't know, we were concerned that maybe people are saying don't know because they're not attentive to the survey. But in the survey design, we sequenced it such that the first question that we asked them was the age of the bus. The second was the bus engine type, and the third was the number of decks. And you see here, this box and whisker plot shows you the percentage of people who say don't know. And for age and number of decks, that most people give you an answer that's not don't know. They tell you it's an old bus, they tell you it's single deck or double deck. So the proportion of people saying don't know is very low. But the question sandwiched in between, which is engine type, there you're getting lots of people saying don't know. So it's not inattention. We think it's likely that there's literacy issues here. People don't know what type of bus they get off. Then we look at the satisfaction questions. Are they satisfied or not satisfied with their rides in terms of the different qualities? And we see that noise is the one thing that people are more satisfied with when they step off an electric bus. So here's a very simple regression where you code -1 for not satisfied and 1 for satisfied, 0 for neutral. And we see that when the bus is actually electric, people are more likely to say that they are satisfied with the noise levels on the bus. Actually, in the interest of time, I might skip forward. This table just really tells you that when people step off the electric buses, if they are also aware that's an electric bus, so they are able to correctly identify the bus as being electric, then they are even more likely to say that they're happy with the noise levels. People who ride electric buses and are aware it's electric are more happy than people who ride diesel buses and are aware that they are diesel. So awareness here increases the satisfaction that you have with your electric bus ride. Right. Yeah, so then what happened with one of the bus lines, 944, the highly electrified line, is that the buses were pulled from that line and moved to a different area at some point in time, and so 944 becomes fully electrified at some point. And there we went back to survey the people to again see how people felt about the noise levels now that their buses were all diesel. And we find that 26% of the commuters said that the bus line was the buses were now noisier. Relative to other bus lines in the neighborhood that were always diesel, only 6% of commuters said that buses were noisier. So people are noticing that these buses are quieter, even if they're not aware that these buses have been electrified. The last bit of our study here is this willingness to pay estimates. So we go to 1,200 residents in the Bukit Batok neighborhood, which is the neighborhood where these 944 electric buses are. And these are the two, very quickly, the two choice experiments we give them. The first is we show them choose option A and option B to get somewhere. The trade-off is that if you choose option A, you get a diesel bus. Choose option B, you get an electric bus. But also there are differences in the travel times when you take these two options. So here there's a trade-off between time and electric bus. And then the second, it's just a trade-off between time and money, right? So an express bus is faster, but more expensive. And putting those two together within a random coefficients logit model, using the estimates, we can pull out a willingness to pay for an electric bus ride, and that works out to be 8.5 cents per ride. Right, so in conclusion, I think it's important to point out here that battery electric buses have different cost structures, right? They're more expensive upfront, but they're cheaper in terms of the energy costs and their maintenance costs. On top of that, there are people who have found that there are public gains to society from the cleaner air. What we add to this literature is the fact that there are also private benefits to electrification that come from, at least in our study, it appears to be from improved noise levels, and people are willing to pay more for that. 8.5 cents per ride works up to about $250,000 more for a bus that's procured over 10 years. So the takeaway here, it's important if you're doing benefit cost analysis for electrification of buses to capture this benefit that is accruing to the users of the bus as well. So it's not just a supply side thing that we should be concerned about. And I think that ends my presentation. Thanks.
Thank you very much. So a question from Julia here. How do you explain the increase of ridership on electrified lines if large shares of commuters are not aware of the engine type? Exactly the question I was going to ask. So please go ahead.
Yeah, so we don't have we don't have a solid evidence here of where that increase in ridership is coming from. What's the reason for it? But the conjecture from the Intercept survey, at least, is that people are aware that it's a more comfortable ride, even if they're not necessarily aware that it's a more electrified, that the powertrain is different, right? So they notice that it's quieter, and so maybe they like that a little bit more. There are some effects that people also, that there are some not quite significant effects, so I don't say this with much confidence, but that the air is also cleaner, and so there are fewer fumes. So maybe that's the thing that's driving it. But yeah, you're absolutely right. It's not the salience of the fact that the bus is electric that's driving it. It's likely an experience thing.
But I think it's an interesting point, because I would assume that the existing commuters experience the cleaner air, experience the lower noise. But the people that do not use bus to begin with, how they will know that the buses are better now, I'm going to switch now from my other mode, right? So
yeah.
It's a very tricky to show like this is not a spurious effect, right? So
yeah, so that's one thing we did look at are there more riders or is it more rides by existing commuters? Because we do have some IDs associated with each ride. And unfortunately there we find it's two things. There are more rides from people who are already riding within the system, but there are also more riders that are joining. It could be a social network effect thing. People ride with their friends or people ride with their neighbors, and maybe that's slightly pushing it a little bit. We're absolutely right that the fact that there isn't salience here in terms of the powertrain does raise questions in terms of if for the new riders coming on, how do they even know that this is, without experience, how are they entering the system? Yeah.
Because I think there is some research that shows that people have, especially people that are the drivers, for example, they're very biased in terms of like their perception of the bus. So that actually the level of service might be actually better than what they think they is. So it's very hard for them to change unless there is like a nudge or something that breaks your habit.
Yes.
But it's very interesting. I'm really looking forward to see additional evidence supporting this.
Great.
And then another question from Julia here. So do the e-buses in Singapore have other additional amenities like USB charging ports or?
So yes, that is true. The new electric buses have USB charging ports, but so do the new diesel buses. So we try to control for that a little bit in this sample, but unfortunately, one of the sort of shortcomings here is there are not a whole lot of new diesel buses within the sample. So when we do control for it, I think I have it in one of these slides. When we do control for age of the bus, you do get that the effect falls a little bit, from 14% to 12%. So the best of our ability, we're controlling for that here. Yeah.
Okay. Thank you very much. So with that, I would like to wrap up this presentation and move on to our final presentation. I think Jintao is here. Yes, he is. So a new methodology for real-time limited stop bus service design problem.
Okay.
Can you share your screen?
Okay. Can you see the screen?
I see your desktop.
Okay.
Okay, now I can see the presentation, yes.
Okay. Hello, everyone. Thanks for coming. I'm a PhD student in HKU, and my supervisor is Warren Sito. Today, I want to talk about my research. Its name is New Methodology for the Real-Time Limited Stop Bus Service Design Problem. There is no doubt that a bus system plays an important role in passengers' movement in a city. In Hong Kong, around 3 million people commute by bus every day. Therefore, improving the bus service level can benefit a great number of passengers. And one effective strategy is to provide limited stop services. So, what are limited stop services? For a given route, normal services can serve all stops of the route, and limited stop services will only serve some stops of the route. In other words, some stops are skipped. Now the question is how to determine the frequencies of the limited stop services. That's the problem, and we name it as the limited stop service design problem. After reading previous papers about the limited stop bus service design problem, we found that there is one important gap left. The gap is that current strategies of providing limited stop services both have disadvantages, and there are two strategies in the previous papers. The first is the tactical planning strategy. With the strategy, an operator does one determination about the limited stop service at the tactical planning level, and at the operational level, and at the operational level, all limited stop vehicles will provide the same limited stop service. The strategy has a disadvantage, that is low effectiveness, because it does not have flexibility. The second strategy is the dynamic stop skipping strategy. The strategy means an operator does not consider tactical planning level. and as the strategy means an operator does not consider the tactical pain level, and the operator does one determination for each limited stop vehicle at the operational level. The strategy also has a disadvantage, that is the requirement of the disadvantage is the requirement of high computational efficiency because the determination is done in real time. The table presents some study about these two strategies. To fill the gap, we propose a new two-stage dynamic strategy. This is a two-stage strategy. As for stage 1, is at the tactical pain level. An operator determines a set of potential optimal limited stop surfaces based on historical travel time and passenger arrival rate. And the set is noted as L. At the stage 2, is at the operational level. For each limited stop vehicle, an operator selects one limited stop surface out of L, and it's L star, based on predictive travel time and the passenger arrival rate. After stage 2, bus captain will drive a vehicle departing from the bus terminal and provides the corresponding service, and the passengers will be informed by mobile phone. When we model the new two-stage dynamic strategy, we adopt an assumption in the previous paper. It's normal and limited stop vehicles depart from the bus terminal alternately. Because of this assumption, when an operator wants to determine the surface of one limited stop vehicle, he needs to consider the operation of 3 vehicles. That is the last normal vehicle, the limited stop vehicle, and the next normal vehicle. These 3 vehicles are denoted as 1 CP. When we calculate the total cost of a series of vehicles, we can divide them into several CVs and calculate the total cost of each CV. The total cost of all vehicles is the sum of total cost of all CVs. For example, there are 7 vehicles. Vehicle 1, 3, 5, and 7 are normal vehicles. And vehicles 2, 4, 6 are limited stop vehicles. These vehicles can be divided into 3 CVs. The total cost of these 7 vehicles are the sum of the total cost of CV1, CV2, and CV3. These are our model. On stage 1, the model is to determine a set of potential optimal limited stop surfaces to minimize the total cost of all CVs based on historical bus travel time and historical passenger arrival rate. In the objective function, D is index and P is CC index. F represents the total cost of 1 CV. Total cost means waiting time cost, in-vehicle travel cost, and operation cost. The model of stage 1 is solved by an ABC algorithm. On stage 2, the model is to select one limited stop surface out of L based on predictive travel time and predictive passenger arrival rate. Each limited stop vehicle is one stage 2. So the objective function of stage 2 is just the total cost of one city. The model of stage 2 is solved by a Monte Carlo simulation method. After the model and the solution method, now I will talk about the numerical studies. To study the effectiveness and the computational efficiency of the new strategy, we compared our strategy with tactical planning strategy and the dynamic stop-giving strategy, and the results are presented in the table. In the table, we can find NL. NL equals 1 means it's tactical planning level, and NL equals 2, 3, and 4 means it's our strategy. NL equals max means it's dynamic stop-giving strategy. From the table, we can find the effectiveness of tactical planning strategy can be low. Only 30%. And we also can find the computational efficiency of dynamic stop-giving strategy is unacceptable. We can see the runtime is very large. And we can see our strategy when NL equals 2, 3, and 4. And we can find the efficiency and the computational. We can find the effectiveness and the computational efficiency are very high. So we can conclude that our strategy is better than the tactical planning strategy and the dynamic stop-giving strategy. They are my references, and thank you.
Thank you very much. Are there any questions? If there are, please post them in the chat. I'm gonna post them here because the sound is not very good, but I might have missed it. But so I was wondering, what are the merits of your proposed model compared to the state of the art in the literature?
Pardon?
I posted on the chat. Can you check the chat?
Sorry, I found this here.
I posted the question on the chat box. Can you read it?
Sorry, can you repeat your question?
So I'm wondering, what are the merits, so the advantages of your model compared to the state of the art? So compared to the best models in the literature, what are the merits of your model?
Merits. Let me see. We did not compare the model with the previous papers because our model is based on our new two-stage dynamic strategy. We only consider the total cost. The total cost is same as the previous papers. The model is different from them.
Okay. Just I probably assume that if you submit this to a journal, a reviewer will ask you, okay, compared to the best models out there, what is the strong point? So maybe further things to consider.
Yeah.
Okay. If there are no more questions, I would like to wrap it up here. Thank you very much to all the presenters. It was a very interesting session. And I would like to invite you to the next session that Ellie is going to be hosting. It's going to be about mobility advancements So if you have time, please stay tuned. And I guess we have 4 minutes for a quick coffee break or toilet break if necessary. And then Ellie, I handed it to you.
Thank you so much.